Hello everyone, this session will be covering overfitting and also the k-nearest neighbor model for agents. Starting off with overfitting, remember from the previous session we introduced the concept of accuracy and error. We define error as given the data training set that we are using and the M model that we have trained, we say that it is 1 minus the accuracy of that data given that model. So if we have error, we have sometimes a problem called overfitting. This is when the data or the error we have on our training data does not accurately represent the error we actually have on our real data, on the true data, as it were. This concept of true data, this is if you were to theoretically have the perfect data that most accurately represents the world, that contains every possible instance that could ever show up, that data, everything you will ever want to classify and ever could classify, that's your true data. So sometimes you'll write D as training. Sometimes T is training, tuning, test. In this instance, we're talking about training data. We also say that the D of true data. True data being everything it could ever come across. Everything it will or could ever come across. Overfitting is a specific example where for some model we say that the error of the detraining given the model is greater than not less than, because we want low error, pardon me, the error of the same training data given some other models, okay, M prime in this case. So it is better than some other model, presumably all other models, it is the best we've found for the training data, but it is also true that the error on the true data given that same model is worse, is larger than the other model on the true data. So here we see that the error on this other M prime model is better, it's lower for the true data. So we're actually trying to solve, this one we care about. The other model is better, but the original model, I put M, that's supposed to be an M, not model, pardon me. But this original model, M, is better at classifying the training data. What's happened is we haven't generalized. We've overfitted to the training data. It's too specific. It knows the training data too well. It's trying to specifically classify the training data. It hasn't generalized. And the point of these are almost always generalization. You have a supervised learning. You want generalization. You want to be able to classify data you've never seen before. Overfitting is the bane of that. It's what you want to avoid at all costs, because it means you have made your model too specific to your trained data. You've taught it too much on that data, and it doesn't know how to handle data it's never seen before. So overfitting is this instance we see here. It's the worst curly brace ever. That's vaguely better. So that's overfitting. If you were to be given the question on overfitting, what you might see, well, there's two types. There's data with noise in it and data with noise free. So a noisy data simply says that there is data there that is the wrong way around it should be. So there's extra information there that's making it fuzzy. It's not quite as accurate as it should be. That's noisy data. Noise-free data means it's as accurate as it should be, but it's still not good enough to train a proper model. What you'll often see is saying you'll often be given a representation of the true data. So you'll be given detraining, and that'll be a table of some sort, and detrue, and you might be saying, okay, is this model overfitting? And you'd have to then find out the error and apply that. It would look something. The result you might get is something along the lines of this. So you have training set accuracy. So this is for some M1. This is for some M2. We see here that M2 is overfitting because it is worse on the true data on the right than it is on the trained data. Whereas our M1, which doesn't get the trained data as well, it's worse on the trained data, is actually really good on the true data. We see here that M1 is the better model, but from the training set, it looks like M2 is the better model because it's just overtrained on that training set. So that might be an idea you have to do. We have to calculate this. using the equations we saw last time on how to find error and accuracy and all the rest. There are two general solutions to prevent overfitting. The first is called early stopping. Early stopping is the idea that you will stop if further splitting is not justified by some statistical test. So you will identify some statistical test you're going to use, and you will do that very occasionally to see if you are actually gaining much significant, for example, gain ratio or info gain, for example, over time. So you'll have some statistical tests to see how much you're gaining by splitting further, because typically you follow Occam's razor, for example. Occam's razor, more complex is bad. So if you have a really, really big tree, it's probably not as good as a smaller tree. So the idea is that you want to stop early rather than late, because late probably means you're going to overfit. The other approach is post-pruning. This means it says that you should grow a large tree, but then prune back the nodes to simplify it. Typically a bit more robust. However, this is used in ID3. Not sure what it doesn't mention what post-pruning is used for, but early stopping is what ID3 uses. But post-pruning is a common method used too. Now moving on, let's look at KNN. So KNN classifies, starting off with just nearest neighbor, which is the simple version of this, with n equal to 1. The idea of nearest neighbor classification is that you will have some graph, and you want to simply say, the training data are just points on the graph. You don't actually learn for anything, you just say points on the graph. And then when it comes to actually testing and using the classifier, you say put a new point in, and then find the nearest point, and say it is the same classification as that point. So if you were to have a graph of triangles and squares, for example, well actually I'm just going to view yellow and blue dots, then whenever you had some other point being put in here, you would then go for all the points, find the closest point, and say that is the same type. So this is now yellow because it is closest to yellow. So if we're presuming that this data has some pattern to it, mine didn't, it would then actually it's not on there. Why not? Or not? There we go. There we go. You would presume that the data has some pattern to it. It's not going to be as randomly distributed as mine was there. But that's how it works. It uses what's called it was a lazy learner. I'm not using a pattern. There we go. Lazy learner. Because there's no actual learning that goes on. Your training data are just points on a graph that you then find the closest one to. And how you find is what we'll look in a moment, but you can find it. The easiest example being if you have numerical data, then you just find the distance, for example. Euclidean distance is one way of doing this, or find what the nearest neighbor is. We use k nearest neighbor to generalize more, because this isn't very good when you have KNN of 1. The idea is you want to generalize more, therefore you want to find the closest, because if you were to have a boundary of points, points here, 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 you have tons over here, and these are the green section. Over here you have the yellow section, very clearly. Then if something spawns in here, it's quite clearly it should be yellow, because all the ones around it are yellow. If it goes here, quite clearly green. But if it goes here, you don't know exactly where the boundary should lie. So if this was not such a smooth border, it might go in and out. So it might point in here really close, and that's all yellow. It might point over here and too. That's all yellow, but there's still a quite distinct green area here. So now the border's looking something like this. So if you had a new point coming in, you don't know exactly what it should look like. Overfitting can happen here as well if you don't generalize enough. Well, something similar to overfitting, where you don't generalize at all, and you end up just having a really jagged line going through your graph, and it's not clear at all where anything should be. So you want to find the balance of smoothing that line out, because that means that your data is going to be more generalized, and any new data you're trying to test with or use in reality is going to be more accurately classified. So basically, there are two steps to a KNN. There's the learning stage and the classification stage. So I'm also using the wrong color, aren't I? Yes, I am. Learning stage. So the learning stage, also still the wrong color. The learning stage states that you just have some training set of X of features. So you have X, Y, up all the way to X, N, Y, N. And X can be any number of features. In this case, there's only one. Many, potentially. You do nothing. You just have the data. You're trying to represent it. You might graph it, but you don't need to. You have the data, and that's enough. That's why it's a lazy learner. You're not doing anything with the data to progress it or to try and model it. You're just having the data. Then there's the classification stage. The classification stage is the actual where the meat of the model comes in. You get given an instance X to classify. What you will then do is find the training set instance of X that is most similar to your training instance. So this is the we say, for example, X of Q, and we're trying to find X I that is most similar. And then what you simply do is classify X of Q equal to X of I. So we say they're nearby each other, therefore they should be the same. That's the idea. So that is just a nearest neighbor. Times when you should be using nearest neighbor, when you have data that doesn't have too many attributes. So the number of features should be less than 20 per instance. So when to use, and you should have lots of training data. So the more instances you have, the better, because that means that you have more to work with. The graph will be more filled in. So that's when you should use it. There are advantages to these. The advantages are that training is very fast, because you just have to put it on the graph. So it's fast to train. You can learn pretty complex target functions, because functions can be graphed. You have a graph of this function over here, which does this. Okay, maybe not that exact function, but something similar to it that comes all the way and over here and smooths up, then all the way up here and goes over here and then down and up and down again, like so. There's a function for that, and you can train it pretty easily. Whereas other models might really struggle to get some complex and arbitrary function, but in your graph, this method can do it pretty easily because it doesn't care. It's just okay. Well, these bits are all going to be the same, so we put something else in. They're going to be the same. As long as you have enough data to define all those edges, you can be fine. You can do it. So you need a lot of data, but as long as you have that data, you can get a lot of stuff. So you need can learn complex functions. It's also lossless. You don't lose information. Lossless. However, disadvantages is it's slow to query. Sometimes you can use particular structures to speed it up, quad trees, KD trees, but even still, they are slow to query because you have to find the nearest neighbor. A nearest neighbor is not a quick algorithm. So given a graph, finding the nearest point isn't a quick thing, so it's slow. And it's easily fooled as well. Irrelevant attributes can mess it up entirely, so you can get very easily can it be fooled into classifying something incorrectly. So you might only works with data that is suitable, as it were. So we've only talked about nearest neighbor so far. Now to move on to k nearest neighbor. This works the same way, but rather than find the nearest thing, you find the k nearest things, and you take the one that happens the most, that occurs most often. So you have a graph such as this. You see here, we can see two circles from here. We are putting in some new thing, x, and if k is equal to 1, then we will have this one, or k is equal to 5, we'll have that circle. So we have two circles. The smaller one is for k equals 1, because it will only choose the smaller, or the closest point. K equals 5 finds the 5 closest points. Then it will run a vote, and the one that shows up the most is the one we classified as. there is obviously here the question of what happens if it's an even tie. If you have k equals 6 or some even number, and all the nearest ones, there are, for example, 3 of one type, 3 of the other type, then you have a tie in your hands. How to break that is context dependent. There's not a set way of doing it. Certain circumstances will have different ways. You could choose the one that find a weighted average of the closest having a higher weight. So the closest has the biggest impact on the weighting on the average, and the furthest has the least impact on the average, and use that. That could work potentially. You could also just choose whichever one's closest. So you have a tie, you go whichever one. K was 1. You could decrement K by 1 until the tie is fixed. Go down to K equals 5, and then you will have to have one which has more than the other. You fix the tie. You might go upwards instead. Go up to 7, for example. So there's different ways of breaking ties. There's no singular way. It just depends on circumstances, and whichever one fits with the data best. One diagram you may see at some point is called a Voronoi, I believe it's pronounced, diagram as such. Where's my pen? There it is. This is a Voronoi diagram. What this does is this simply shows that all of the possible regions in the graph, so anything that shows in this region will be classified as this point. This region, this point, this region, this point. Anywhere in one between the edges, the point that defines that polygon, 2D, would be classified as that neighbor. For this case, k equals 1. So they show the nearest neighbor for each, the nearest neighborhood, as it was. They define the neighborhood that has particular neighbor involved. Everything we're looking for is a 2D graph because they're nice and easy to show, but as we mentioned, when to use these things, they don't have to be limited to 2D. They're nice and easy to view in 2D, but you can have, like I said, as many as you want. It's just as you start getting more and more, the amount of processing power to represent high dimensions gets harder and harder to find, so it gets slower and slower and slower. As it were, you typically want to stop before 20, though it depends on your hardware. Sometimes you need to go lower and lower, even further. You might want to use dimensionality reduction, for example. But yes, a Voronoi diagram simply shows the nearest neighbor. So if you were to ask a question, say we have a point here, which is its nearest neighbor, you can then use a Voronoi diagram to find that out. Now that we've had the sort of informal introduction, let's look at a equation that describes all of this, all of what we've said so far, which is this. And this can be read as just return the class or classification that has the most number of instances in the thing that we're looking at. We say here, pardon me, yes. So we have this, which says basically, once we've already found the nearest neighbors, we can go through each one and identify if they match. So if we're saying, remember, argmax is a function that returns the arguments that provides the maximum, and we are trying to find the maximum. We say for the classification, we try remember y is the classification. For classification, we're trying to find all possible values of it. Yes, no, for example, square, triangle, apple, orange, whatever. For each of those, we want to find what this function we've defined here, which is just saying that it will return 1 if the two arguments are the same and 0 otherwise. We'll go through and identify all of the ones which have matching, which match. We'll sum those values, so you have a 1 plus 0 plus 0 plus 1, for example, if you had 4 things, and you'll go through. So in this case, since we're going through I 1 through k, we already know what our closest nearest neighbors are. Now we're just identifying what classification it should be. So this is the classification equation. How exactly we find the nearest thing we'll be looking at in a moment. But this is an equation that does that. So if you see this, it's simply saying, how can we classify the current thing? For example, you might have something which returns, you might have 0 plus 1 plus 0. That's going to be 1. So that might be for yes. And then for no, it might be 1 plus 0 plus 1, which is 2. And because you're doing argmax, the arguments, so the values of v and y, which is what we care about, will be what it returns, which will be what's stored by y, and that will give us the v is what we have, will give us which of these ones we want. In this case, no. So the v that got the no will be the one we look at. So yes, that is how we can classify. Now let's look into how we can identify similarity. So we need some way of measuring similarity. So a similarity measure. So similarity measures are how we can determine the distance between two things, or how similar they are. Euclidean distance is 1. We looked at a few of these already in the first session, but things like L1, which is Manhattan distance, L2, which is Euclidean distance. There are others as well. If we see, what was the equation for it? It's around here somewhere. There it is. Yes. So in linear algebra, we have this concept of a norm, and norms are very similar to distance measures or similarity measures, or whatever you want to call them. So, for example, we can find the distance of multiple things. We're finding the sum. That's not how you do sigma. The sum of the size, so for every single thing in a vector, for example, which is how we can represent instances. So we might say for I in some vector x, for some instance x, we can say the value of x of I raised to the power of something, so 2 for example. And then over that we can take the result of that sum. We can then do this, which is the equivalent, not p, 2, which is the equivalent of square rooting. To the power of a half is the same as square rooting. We can do it again. For L1, we just don't square and we don't square root. Well, we don't raise to the power, or we don't root to the power of 1 because it doesn't do anything. But it is a similar thing. So yeah, so Manhattan distance, Euclidean distance are common distance measures for numeric data. Manhattan distance also works for non-numeric data because it simply says how different are these things, or rather, how many things in this feature, in these two features, are differ. So you have, that's a H. You have A, B, and C, and you have two things A and B. This is H. This is J. This is F. This is also F. This is M and N. In this case, they have a similarity of 1. They have a difference of 2 because these two, this one does not match. So you can use that, for example, to figure how similar two things are by identifying how many things they differ by. So similarity measures are very good and are required for a k-nearest neighbor to figure out what is nearest. The idea would be that you would take whatever one you have put down in your graph, whatever new instance you have, you would then compare that, find the distance of every other one, order by distance, and then select the closest, or k closest, depending on what k is. So with all of that, we can now move on to how the k nearest neighbor learns. And it learns by selecting k. So what it will do is it will using its training data and its test data, it will be able to classify its test data, figure out how accurate it is for a variety of different k, and it will select the k that minimizes its error. So that's how these things learn. And by doing that with tons of different k, it can then select whichever one is the most accurate, which is best at fitting the model with its test data. Problem being that if you have very high dimensional space, if your graph has a large amount of possible variance, or if you have continuous variables that have a large range, then the space between them can be very large, and therefore nearest neighbor might not be very near at all, meaning that it might not be all that similar. Could just be that there's not much in that area of the graph, and they just sort of selected the nearest one, which was still ages away. Also, while you are choosing k, as you increase k, you reduce the variance, so you're allowing greater generalization. You're just increasing a bias in a way, so to be careful with that. So you have to be careful of those two things. Also, if we look forward, we can see the problem with The problem with these things is that they have to store the entire graph of data. So they are best with large amounts of data, but that data needs to be stored at all times. And potentially you have to add more. If you are confident in a particular classification, you could arguably add it to the model. But models with a lot of data take up a lot of memory, and you don't want to store them all the time. So these things do take up a lot of memory. And the larger it is, the more accurate it is. So it's a trade-off between how much memory you can spare all the time. And of course, the bigger it is as well, the more time it takes to go through, because you have to find measure for all of them. One way we can improve this in specific circumstances, for example, if n is equal to 2, then we can use a Voronoi diagram. And by storing that in a very particular way in memory, which we don't get into, you can produce something along the lines of this. Well, the diagram looks something along the lines of this. And when we have that, and we spawn in, and we say, okay, we have a point being made here, then if each of these is stored in memory as its own little thing, we can very quickly determine, oh, this is our nearest neighbor. So if you have an n of 1, very easy. N of 2, you could just look at all the neighboring polygons. We see this, and this, all neighbor the place we came into it in. The place the new instance spawned in is neighboring those ones, so we can ignore all of these ones everywhere else. And by that, we can reduce the potential complexity, so long as you have a way of doing that, which some what's the word I'm looking for? Some data structures can. If you have more than if you have n is more than 2, though, you start running into problems, and typically n is almost always more than 2. The Voronoi diagram starts becoming less useful. It starts becoming exponential. You have m to the n with so you end up having problems. So rather than that method, what we can use is called edited. An edited edited nearest neighbor. So edited nearest neighbor simply says, we don't need all our data, let's get rid of some. Similar to compression, we're basically going to get rid of the things that don't impact the overall graph very much. If you look at, for example, if your graph looks like this, where you have a bunch of things in this area which are all blue, and they define this border like so. You have another one over here which does this, which defines very distinctly there's a border here and a border here, and all of this is like so. There's another one here which is defined like so. Again, very distinct borders in this. We can draw them on. We can say, okay, there's clearly a border going in here. There's another border going here, like so. And for example, with a higher k, for example, this might get ordered over. You wouldn't actually have this little indent. Is an example of the things a higher k can do. Point is, in this, if something spawns in this, even with a huge k, it's not going to be yellow, it's going to be blue. So unless you're operating in huge numbers of k, you can probably get rid of some of these, since you're still very in the depth of blue space. So all these ones that are miles behind the border, they're not going to have a huge impact on anything. Therefore, they can be pruned back, they can be taken away. They're going to have a huge impact. Same with up here, the center of this green space as well. So only really the border ones that you define, because they're the ones that define the border cases, the edges of the space. So they're the ones where the classification changes. So they're the ones where you need the most to be able to enforce that border. As long as you have a strong border, it doesn't matter if there's not that many inside. So you this is called edited nearest neighbor. There is simply that you remove, you incrementally delete things and make sure that it doesn't affect the accuracy too much. There's another approach to this is rather than going from the full thing and selecting instances and checking if it still classifies without them, you can also do the opposite, where you go. That's called incremental growth, where you remove. That's wrong pen. Incremental growth. Sorry, incremental deletion is where you delete things. Deletion. Incremental growth is where you go the opposite way. So you sort of an empty graph, and you start adding things based upon how whether or not it doesn't accurately do. So you say, here's this instance I'm thinking of adding in. Does what we have already classify it correctly? No, it doesn't. Now we need to add it in, because clearly it's not good enough yet. So you add it in, you go on to the next one. Does it classify correctly? No, it doesn't. Add it in. You keep doing that until you've gone, and you only add the things in which are correctly putting in. And of course, order matters here. The order that you try delete things or you try add things will affect it. So this could be a large chunk of learning. We're trying to identify which of these you need. So there's another effect of these things can learn. Well, learn in a way. It's where it's actually learning. It's more becoming more efficient and reducing the amount of memory. But it's still going to improve over time. But hopefully it wouldn't actually affect the outcome too much, because you don't want to affect. Because the more data, the marker it's going to be. So the effect it would have really would make it worse, and we're trying to avoid that, because this is called incremental growth. That's not nice about growth. Growth. Still nice about growth, but close enough. That's one way we can do it. This is nearest neighbor. Another is called a KD tree. Basically, a KD is in 2D, 3D. K is in K dimensional. So a K dimensional tree. The way a KD tree works is it splits up a graph. So if we have a graph such as this, I'm actually going to take a moment to draw this out separately. Here we go. So when we have a graph such as this, a KD tree is formulated, is constructed from this graph by selecting the point in the graph with the greatest variance. This means that we're trying to find the point that, when chosen, will split the graph in the greatest way. So what I mean by this is, if we select F and we draw a line perpendicular to the x-axis, from F we get 1, 2, 3, 4, 5 points to the left, and 1, 2, 3, 4 points to the right. So F will be our bridging factor. So what we're going to say is, when this is the x1 axis, this is the x2 axis, this is describing an instance with two features. When x1 is 6, we want to have so when x1 is greater than 6, we want to go to the right, and otherwise we want to go to the left. So and this is the point for F. So if we're searching for F, we will go to this point. So we're searching for the point which is what was I saying? Yes. So if we have sorry about that. I pulled the wire out of my headphones and gave myself a jump scare. Hopefully I'll be able to edit that out of the recording. Yes, so we split upon a particular point. In this case, we say that F has the greatest variance when split along the x1 axis. We get 4 things. And then what we'll do is we'll split across the next best axis for the other two. So we basically split the graph in two. This is now its own subsection. That was not a pen. Of the graph over to the left, and this is the right. The entirety of the left is accessed through this left path, and the entirety is right access the right path. So you're trying to access J, for example, you go to the right. So let's start with the left. How can we split the left with the most variance? Well, if we split along we can't split along the idea is that you split along the same axis, or the opposite axis. But if we were to split along C, we see here that on the wrong color, green, say for example here, then we'll have 2 above, 2 below. So C has high variance. We potentially could do D, for example, because that puts A to the left and B and C to the right. But let's use C. So that means that C is to the left now. So we put C to the left, and we're going to have that's on 10. So x2 is greater than 10. That's the path to A and B. If it's greater than 10, we can start going to A and B. This is the path point for C. We go to the left, then we're going down below 10 on the x2 axis, down to D and E. And that's due for the right. What can we split on the right? If we look at the H, we can go also perpendicular to the x2 axis. we can say, if we say x2 is more than 5, which is roundabout where that is, then we split 1 below, 2 above. It's an even number, which means splitting on 1 is going to cause it to split with an even number on both sides, an odd number on one side, but that's fine. So we go to the left, it's going less than 5, which means accessing G, and to the right, we're going more than 5, so I and J. And we can move on and on and on. Now we can, for each of these 4 subsections we've now got in, these 4 quarters, we can go further and further and further. So we can split greater and greater. And the idea is eventually you will have everything split in such a way to have it where everything is on its own line. So you continue on. For example, after C, we can then split further on E. So E could then be split. Okay, well, we can just split this way. E will go like this, which means that E's point now is for x2 is greater than 4. And if A went to the right, then that means we're accessing D. And how can we split D? Well, we can say, for example, we can split D here. We can say D is for x2 is greater than 4. It should be for E. This is for D. So if you go to the right or the left, you're not actually accessing anything else. It's a leaf node with nothing in it. And if you go left on E, there's nothing in it. So now, if you're trying to add an instance, you will put them in one of these leaf nodes. You will eventually go all the way straight to this point here. Well, that point is 2, 6. So we can say it's x1. We look at x1. 2 is less than 6. We go down to the left. 2, 6. That's going to be less than 10. We go down to the left. It's 6 on this, which goes to the right. And it is... Why did I put x2 is 4? That should be x2 is 8. Pardon me. x2 is greater than 8. 6 is less than 8, we go left. So now we put a new point here. And through this are algorithms we can use to find the closest point. That's how you use one of these trees. And we'd have to do all the rest for everything else as well. And eventually you'd have a graph for this particular instance that looks like this. So the full thing would eventually look like for that particular graph. And each leaf node would be the particular point. So when you're adding instances, you'll put them in those nodes, and there are various algorithms we can use to find them. And there's a point. This is not the only way to construct a KD tree. It is one way. This is the way we have to care about. But there are others. Let's have a look at an example of how we could query such a KD tree to find if what the nearest neighbor was to a particular thing. So we're using the singular nearest neighbor, n equals 1, just for simplicity. But this would work for multiple neighbors. You have to keep track of more information. So let's see, we were looking at the position 2, 3. So 2, 3 is this position here. We're looking at this. We call that Q. So we're trying to query this, trying to get a prediction of what the nearest neighbor of this is. We're trying to predict it based upon the classification of what the nearest neighbor of this is. You know what I mean? The process for this is we have to use the tree. So we'll be using the pictured tree over here. We have to find, based upon f, which one applies. So remember, this is 2, 3. This is x1. This is x2. X1, 2 is less than 3, so we're going to be going to the left. So we're going this way. X2, we're going to the left again. Remember, so what we've done so far is we are now looking at this section of the tree. So we're ignoring this section. And then here, looking at this case where x2 is greater than 10, so we are now ignoring this section of the tree. So we're slowly putting the tree smaller and smaller. And this section here, we're going to be looking at further. So I'm not actually going to go there because we will have to look in more detail later. So x2 is more than 4. It is. So this is representing E. So we now. I said it's. Oops. No. X2 is not. It is a 3, not 6. So it's going to be going here. So we now get rid of this section too. So going to the left. Now we have hit this section. We're going to the left. We've hit a dead end. So there's nothing to do left. So we've hit the end, and we found that. So what we'll be doing all after that process, for every node we reached, we would have to find, we had to keep track of 2 bits of data. The distance, the sort of shortest distance we found so far, and the node of shortest distance. And every single time we found the node F, C, E, we'd have recalculated the distance every single time. And we keep doing that until we had reached this leaf node where we didn't have any more nodes to explore. So now we will have had some value of what the distance from Q is to E. The next process would be to look at the next possible path down and see if it could ever be possible that it would have a closer value. Because the distance between Q and E, we're looking at this, so E is 2, 4, so 2, 4, which distance measure you're using matters, but for example, you could do Manhattan distance, which I believe would have a distance of 1 in this case. Euclidean distance would be the square root of 2 squared, 0 squared plus 1 squared, depending on which order you went to. Whatever, Euclidean distance of those two would be a distance as well. Whatever distance measure you're using doesn't matter as long as you're consistent about it. So you would have some distance between, in this case, Q and E, because that would have been the shortest. So E and the dist of Q and E, what we currently would be working with. The idea is then, from this point, we know we're not going down this way because we've looked at that, but we would still have to double check that there's definitely no possible instance where there's something over there that could be quicker. So what we'll do is we will draw a straight line between our thing and the border that D defines, which happens to be, well, it happens to run along. So we run along straight into that and find the distance between that imaginary point, which again just so happens to impact, but D could be over here and it wouldn't affect anything, or Q could be over here drawing a line up this way. It doesn't matter, as long as it's hitting this line. You will then find the distance from that to that line, because if theoretically there was something in this region that was closer to Q than E, because remember the computer doesn't know where these things are, it just knows that they're near. So if theoretically there was something closer to Q than E, it would have to be at that point, because you look at a circle, that's going to be the closest point for that distance. That there is the closest point that Q could have. So we have to look at that point. If the distance of that point is smaller than the shortest, then you have to explore that bit of the tree. If it's not, you can prune it. So you prune that bit of the tree. In which case now we can see that distance is much bigger than the distance to E, so we prune it. We don't explore that path. And we also do that for the rest as well. So we'd have to do the same in B. B would also have to be pruned. And so on and so forth. So you would continue pruning like so each time. So this would get pruned as well because B is also up there. There's a question of F. Do we have to explore any of the right-hand section of the tree? Because theoretically there could be something. If E was just a little bit further up, then this point here, right next to F, could be closer than E, even though we ignored it at the start. So now we have to go back through it again, check if that's any closer. So we will then check if we draw an imaginary line to that to this plane here, along this the point of 6. Is that point closer than E? We can see it's not going to be, so we prune the entire right side of the tree. So that's everything we've done so far. E is the nearest neighbor to Q, and again, that would continue happening. If you had other things, you had to keep track of just more information and do the process a bit more, because you will have to potentially find that once you've done F, there might be other things in that part of the tree which are closer. So a higher end just means a bit more complex in the amount of data you have to track. There is a variant of a KNN classifier. Go up here, somewhere at the top. That KNN classifier called the KNN regression structure. Regression. That's probably spelled right. Make that green. I think it's another section I forgot, pardon me. So yes, the KNN regression is a similar thing in how it's structured and the data you give it, but you instead have to find you use this algorithm, which basically you have to average the neighbors' values. So rather than classifying the same as them, you will, saying the classification they have, you will then instead take the average of all of their values. You use this equation. So y is our return. We will then say we will return this thing here. So we will do basically sum up each of their values and divide by k, which is the number of values you have. Same thing though, it's this same type of thing. Sometimes as well, rather than doing this, you would want to divide by a weighted average, so the closer things have a higher impact as well. And that's the same as an expectation, and it's calculated pretty much the same as well. You you have to then incorporate the distance as part of the weighting. So you'd have to do something along the lines of, where's the equation? Why can't I control my mouse? There we go. This equation here. So we see here, you do the sum of their weightings times by their value divided by the sum of their weightings. And that will give you the weighted average instead of what you have before. The reason you have to divide by the weighted is because the weightings are normally, if you do a weighted average, for example, for probability, the expectation, the numbers are between 0 and 1. They are ratios. In this case, here you have to find the ratio as well. So you do the ratio, basically, of y and the weighting, and then times that by the weighting, which is what your expectation usually is. And that will give you a distance weighted nearest neighbor, and again for whatever value k you have. And we typically define the weighting as the reciprocal of the distance. That's another point. But it's not always the distance directly. It can be, for example, wi can be equal to 1 over the distance, so d, of sum x q, which is the thing we're looking at, and xi, which is the instance we're looking at, squared. One thing I have to be careful when it comes to any type of KNN tree, classifier, or regression is when you have irrelevant features. So for example, you can have these two environments, these two graphs, like so. They are both describing the same feature set. However, one is in 2 dimensions, the left one is in 2 dimensions. This is 2D, this is 1D. I'm in the wrong color. So you can see how they line up. We have one here. These two are very similar in where they're very close together, but they have a lot of data there. So x2 is an irrelevant feature. So x2 is irrelevant. You can accurately predict this using just x1 on its own. Having x2 reduces the accuracy. There is a point here-ish where if you have just the x1, it will classify as red. Whereas both, it classifies as x2, and the correct point would be red. It is closer to x2. You see this line here-ish is closer to x2 than it is to this one. So it should be classified as red. But because x2 provides a greater distance between them, it is actually going to classify them as green. So irrelevant data is a problem that can often be run into for these types of classifiers and regression models. A solution to this was what's called locally weighted regression. The idea being that is you weight features differently. So you can say x1 has a much higher weighting than x2, because x2 could be adding things. It could be important, but not as important as x1. So x1 is very important, x2 is only slightly important. So you'd basically squish x2 down, as it were. So flatten the entire graph, not to be quite 1D, but only so it has a little bit of dimensionality. So the differences between that are much smaller, meaning these two we can much closer together, and hopefully it would be enough to impact it enough and cause the the red classification to win out in this instance. That idea. So you're trying to. This is called locally weighted regression. And yeah, it is a regression method, but I'm pretty sure it works for classification as well, so long as you have a you change your distance measure to have a weighting, so that you weight one axis more than the rest. The idea is that you have a function part of the learning process. Now you have to find this function that is able to incorporate those weightings appropriately. So you have, for some instance x, you will apply f of xi. I suppose that should be subscript. Don't know whether to have it in superscript. It's not, you're taking it to the power of I, which is equal to a bunch of weightings multiplied together. For example, we have weighting 0, weighting 1, and also x1, which is part of I. You have weighting 2 of x2. You're going to multiply them together, add them together, and all the rest, up to eventually the weighting n of xn. So the nth feature is going to have the weighting, it's going to have this weighting, and so on and so forth. So if this was very important, then this weighting could be very high, with the others being very low. And the idea being that this would then allow this to have much more power over which feature, or which result is then chosen. In this case, you're only going to be releasing there's a regression, so you want the values only, so it is the same as expectation, or weighted average. What we've been talking about so far is called instance-based learning. There's a lazy learning, as it were, where the model is just the trained data itself, with very little actual learning being done in the learning stage, and most of it just being done afterwards when it's live, as it were. So it's strong. It has strength. It's simple to implement. Training is typically quick. And it is useful for online learning. Remember that concept, online learning. It fits well in that. And so long as you have a sufficiently high K, it is fairly robust against noisy training data, because it can sort of generalize pretty well, and it is typically good at what it does. However, it is sensitive to a range of feature values. So if you have too many values being allowed, or if you have too many too many features at all, it becomes sort of too high dimensional, and it's no longer efficient to use. And irrelevant or correlated features cause it problems, though there are ways to do that. So what we just explored, which is locally weighted regression, which can alleviate that problem. Is also the fact that it can be inefficient, though there are things like edited methods and K-trees which help alleviate this. Again, it depends on these extra methods. Sometimes it will still be too slow. And they don't provide too much insight. They are useful, but they don't provide insight on what's going on. So if you're trying to use this as a sort of research tool, they're not great. Functional, but they don't give much information on their own. That's everything for this topic on decision trees and the brief foray into overfitting. I hope this was useful. I was experimenting a little bit more this time on using pausing and stuff to try and speed up the writing stage and things, so there's less downtime. I hope that was useful. Interesting more feedback I can get on that. Good luck on the exams. I'm hoping that everyone does well and that these sessions are being useful.